Hello, lovely people. How's everybody doing? Did everybody enjoy their bank holiday weekend? Can you guys tell when it's a bank holiday weekend, even though it's sort of not much of a schedule at the moment, I imagine, for your days? How's everyone doing? We'll get started in a bit. You just sort of wait for a few more people to pop in. Just give me 1 second. So my lovely colleague has dropped the slides in the chat. So please go ahead and download those if you want to sort of, because we're dealing with NMR, we have sort of scales on the axes that will be a little bit tricky to see on the sort of YouTube size box. So it's a good idea for this class to download those, because otherwise it's going to be tricky to see sort of like the values. So do have a go at that too. You made a coffee too? Yes, Namrata, I'm all for caffeinating. As last time, so this is sort of like part 2 of the NMR stuff, and then we're not going to do any more NMR. So this is sort of like year 12 friendly if you showed up to the last one, or if you sort of got a little bit of previous knowledge about NMR. So this, because it's a part 2, right? So like if you've never touched on NMR before, it might be a bit tricky. Or it's year 13. So year 12s that turned up to the last one, or have come across NMR, or year 13s, this is suitable for. I don't want to get started too quickly because I don't want, I'll just sort of slowly open the presentation, and then you guys can, will there be a session on NMR questions, or is there just going to be these? For now, we're not going to do one on NMR questions because there's sort of like not that many people who have covered NMR yet. So the year 13s that have covered that, there are lots of year 13s that haven't covered it because they weren't in school or college or wherever when it sort of got taught, because lockdown had already started, and also year 12s, unless they were in the last one, haven't covered it yet. So doing questions is a little bit sort of jumping the gun a bit. So what we will probably do is at some point run through NMR exam questions, but not immediately. Does that make sense? Sort of like the reasoning behind that. Oop, I'm malfunctioning. There we go. Oh, it doesn't like me. Oh no. Just 1 second. I'm having a bit of some tech issues. Of course, because computers never like me. Why do this? Okay, it hates me. Oh no. Sorry, people. Let's just see if I can get. Nope, it's just gonna hate me. All right. Well then, is this a lesson or just questions? This is a lesson. So this is sort of part 2 of the lesson. Were you in the last one, Momina? Is that how you pronounce that? Were you in the previous one? Okay, let's get started. All right, so the idea of today is that we're going to be looking at proton NMR splitting patterns. So our proton NMR splitting patterns are a little bit trickier to interpret than just the NMR peaks, which is why we're sort of doing a whole thing, having a look at them. So we have, as usual, a coupon code to give away at the end for you guys to sort of get our website a little bit cheaper. So hopefully you guys, if you want to stick around for that, you can. I'll also be sort of showing you around our website a little bit. Hi, Ikra. Okay, so without further ado, we're going to get started by sort of reminding ourselves of like the stuff we already know about the sort of the spectrum itself, and then we can move on to sort of analyzing what those sort of like clusters, these splitting patterns are, and what we can sort of understand from them. Okay, so does anybody remember what each sort of peak or sort of collection of little peaks tells us? So we covered carbon 13. We're going to be talking about hydrogen at the moment, but does anyone remember what those little peaks tell us? Sort of just like the number of the peak on the x-axis. Hello, everyone. Yeah, the environment of the peak. So on the sort of H plus, that should be an H, on the proton spectrum, it's going to tell us about the proton environment. And if I keep saying proton and you're confused, just keep in mind that a hydrogen plus ion is a proton. And that's just because hydrogen only has one proton and one electron. So if it's an ion, then it's just a proton. Yes, so that is the chemical shift. So thank you, Kang, for telling us that. So the chemical shift is telling us about what kind of environment the proton is. So if you have a high chemical shift, what does that mean about what the hydrogen is bonded to? Any ideas? Yeah, it's bonded to something more electronegative. So the higher the chemical shift of the proton environment, the more electronegative. Exactly, you guys remembered perfectly. The adjacent atoms are. Yeah, exactly. It's bonded to more electronegative atoms. Okay, so when we're looking at the area under the peaks, what does that represent? So if we remember that the height doesn't really tell us much, but the area under the peaks does tell us something. What does the area under each of the peaks tell us? Or each sort of collection of peaks, like a cluster? Kind of the frequency, yeah. Anyone got sort of like a more detailed response? Yeah, the number of H pluses in each environment. So the number of protons in each environment. Cool. So chemical shift measured in parts per million, which I won't go into too much detail about. So the tricky thing is obviously just looking at a graph, it's going to be very difficult to measure the number of the sort of area underneath each of those peaks, right? Anyone that does maths, how do you measure the area under a curve? Does anyone remember sort of from maths? Will this topic be covered in September year 13? Do you mean on our platform or in college? Yeah, integration, exactly. And luckily, the software tends to do the integration for you and will either give you a number or you'll get something called the integration trace. So essentially, whoops, that's a rubbish line. Okay, I'm going to try again. Essentially, the software will give you sort of a line for each peak that shows you its relative abundance. So roughly, the one I've tried to draw for the integration trace, and you can measure it with a ruler in the exam, or it will just tell you how many numbers there are. That should roughly be sort of like 1 here and 3 here. So that peak on the left should account for sort of 1 proton, 1 hydrogen, and the peak on the right should account for 3. So that sort of gives you an easier way to sort of measure the area. Is everybody following me so far? Yes, no, maybe, I hope so. Yeah, okay, cool. All right, so we're just, before I sort of move on from this slide, we're going to sort of, without thinking about the splitting patterns, just try to identify which peak belongs to which. Do you need to know the integration trace for OCR? So the integration trace is just the area under the peak. So either you'll get a number or you'll get sort of a curve that shows you the number. So that curve is an integration trace, and all that's showing you is the area under each peak. So it's not, it's literally just like, you can tell that there's sort of this line up top, and I'll sort of try and draw it a bit better, is about 3 times the size of this line. So you can get 3 in there. So all that's telling you is there's 3 protons in that environment. It's not, is that just to show the ratio? Yeah, exactly. It's just showing you the ratio between the protons. So either the exam question will give you that, or it will give you the just literally the numbers for proton and NMR. Why is TMS so small? Since it has 12 protons. Chances are that that's a good question. Is that trace given to you always? Okay, hang on. I'm going to go back to the last question. Why is TMS peak so small since it has 12 protons? Possibly the software tried to cancel out the TMS peak, and therefore it's small like that. But I'm not entirely sure. But you don't ever need to analyze the TMS peak. So I'm imagining that the software would try to get rid of the TMS peak. It's not always there. So if you see something at 0, you don't need to. Is the trace always given to you? No. So sometimes the trace is given to you, or sometimes it just tells you the numbers. Is the TMS solution dilute? So the TMS is a reference sample. So for example, the NMR spectrometer may already be calibrated to TMS. So it's sort of not so much about like you in a lab also putting TMS in your solution. Tetramethylsilane derived from CDCl3 are used in small amounts, so the peak is small. So the concentration should not affect your NMR. So the concentration of something in your solution shouldn't affect the NMR spectrum, unless, of course, the NMR spectrometer can't actually observe the thing that you're testing. How do we know that TMS peak has 12 protons? You don't need to analyze the TMS peak. The person who said that is just sort of realizing that TMS stands for tetramethylsilane. So if there are 4 methyl groups, then that must be 12 hydrogens. But you really don't need to, all you need to know about the TMS peak is that it's the reference peak. It's the peak that sort of sets the chemical shift to 0. You don't need to analyze it at all. What do I mean by software? So of course, the NMR spectrometer is going to have software to produce these graphs. So that's what I mean by software. So the graph doesn't just like appear from the NMR spectrometer. The NMR spectrometer is hardware, but it must use software to produce graphs. What about solvents? I'm not going to cover solvents today, just because I want to just sort of focus in on interpreting graphs rather than sort of understanding the background. It's a really big topic, so I had to make choices about what I was going to do on YouTube, essentially. Okay, I'm going to move forwards if everybody's good. And we should be fine. And the person said that the internet froze, and I can't remember who said it, but the person who said the internet froze, can I go through this slide again? This slide is a lot like the carbon-13 stuff, so you should be okay, because I know you were in last time. And the next slide is kind of consolidating that stuff, so you should be okay. All right, so we're going to really quickly just look at this NMR spectrum for butanol and try to decide, just based on the number of proton environments, which isomer of butanol we have. So how many isomers of butanol exist? Someone sort of give me some isomers of butanol. I'll explain labile in just a second. How many isomers of butanol? Yeah, we've got butanol, which has the alcohol group, oops, that should be a 2, which has the alcohol group on the end. We have but2ol, which has the alcohol group on one of the central carbons, and then as Mushafi, if you could help me pronounce your name, I would really appreciate that, but you don't have to, of course. Or you could have 2-methyl propanol. So we would have, so it wouldn't be 2-methyl propanol, it would be 2-methyl ethanol, but I think I know what you mean. So, or we could have sort of like a central carbon, or this would be, oh no, sorry, yeah, my brain's not working, 2-methyl propanol. Yeah, or this isomer. So the first thing we want to do to tell which of are there only 3 isomers? Yes. The only thing we're going to do to tell which of these butanols is in our NMR spectrum is just look at the proton environments for now, and then in a bit we're going to have a look at the splitting patterns as well. So the reason I put on the top no labile H is because the protons, the hydrogens on the sort of the hydroxyl group, on the OH group, they don't always show up in an NMR spectrum. And if they do, they can be very small and just sort of like anywhere. Like it's not, the problem with those hydrogens is that they can sort of come off in solution really easily. So they're not always in the spectrum. And if they are, the peaks tend to be very small and not related to the electronegativity necessarily. So by no labile H, all I'm saying there is like this spectrum does not include the hydrogen that's on the alcohol group itself. So we can ignore that one. Can I please tell me how you would tell you how I would identify it? Yes, that is what I'm about to do. Cool. So we have our 3 isomers of butanol, right? So let's just sort of go through each and decide how many proton environments there are going to be. So with our butan 1ol, our primary butanol, how many proton environments do we have, ignoring the hydroxyl one, ignoring the alcohol one? Because again, we've said in this spectrum, there are no hydrogens from the hydroxyl group. Any ideas? How many proton environments do we have for the first butanol? Getting some different answers. Anybody else want to weigh in? Oh, there is, thank you. Yes, you're right. You're totally right. There is a mistake. I appreciate that, Musafi or Mushafi. Please help if you would like me to say your name correctly. I apologize. Yes, there should be, I really appreciate that. There should be 4 carbons in there. Yes, cool. So for the butan 1ol, we actually have, we should actually have 4 carbon environments. Mushafi, is that right? I hope that's right. So we should actually have 4 proton environments. We have 1 proton environment here for the protons that are attached to a carbon that's attached to an OH. We have another proton environment here where the protons are attached to a carbon which is attached to a CH2 that is attached to an OH group. So you still get some of that electron withdrawing effect. You still get sort of like the electronegativity of the oxygen still affecting the CH2 that's sort of not even bonded to it. my face is covering that part. I'll talk about that in just a second again. Namrata. And then this proton environment is technically very slightly different from the protons next door. So the point is, unless the molecule is perfectly symmetrical, the proton environments are different. So unless it's perfectly symmetrical, like one of our isomers down there, technically the proton environments are not the same. In sort of low resolution NMR spectroscopy, the peaks may be so smushed together that you can't tell the difference. But in high resolution, so high resolution being anything with splitting patterns, you will be able to tell the difference. So people are asking me, what does labile mean again? What about the proton in the OH? So labile, the word itself just means sort of like changeable. And a labile hydrogen is usually one either on an alcohol group or an amino group or a carboxylic acid group. It's a proton that can sort of like come and go quite easily in solution. And because that hydrogen in the alcohol group sort of leaves, it like falls off the oxygen and reattaches quite regularly, sometimes it doesn't show up in the NMR spectrum. And even when it does, it shows up in really random places and it doesn't have any splitting patterns. Or contribute to splitting patterns. So that's what labile means. So all I'm saying is this NMR spectrum does not include the hydrogen, the peak for the alcohol hydrogen. Cool. So we have one butanol sort of on the top that has 4 carbon environments. What about the one below? How many carbon environments does butan-2-ol have? Hi again. Yeah, 4 again. We've got 4 carbon environments again, apart from the labile, sorry, hydrogen environments, apart from the labile one. So we've got 1 here, 1 here, 1 here, and 1 here. So the sort of number of environments is not helping us cancel one of those out, but we'll talk about those in a second. What about the last one? What about the 2-methyl propanol or 2-methyl propan-2-ol? Is labile always addressing OH? No, the word labile literally means changeable. So like it can be used in other subjects too, not just chemistry. So like you could have a labile egg, like the eggs for reptiles, and that would mean that the egg sort of was changeable depending on the environment it was laid in. So labile just means sort of changeable. It looks like 2, yes. So we should really only have 1 proton environment for our 2-methyl propanol. So this is an example of a symmetrical molecule, right? Because these protons are bonded to a carbon, which are bonded to 2 other CH3 groups and hydroxyl group. And it's the same with these protons. These protons are bonded to a carbon, which is bonded to another carbon that is bonded to 2 other methyl groups and a hydroxyl. It's exactly the same environment. And the third one, it's also exactly the same environment. It's 3 protons bonded to a carbon that's bonded to another carbon that is bonded to 2 methyl groups and a hydroxyl group. So all of the protons in this molecule are in the same environment. So we only have 1 proton environment except for the hydroxyl proton, which is not included. So we can basically sort of say straight away that it's definitely not that one, right? Why is our NMR spectrum? Yeah, we don't just have 3 in the same environment, we have 9 protons in the same environment. So we just have 1 really tall, 1 peak with like, there'd be a lot of splitting because there's a lot of coupling, and we'll come to sort of what that means in a second. But there's only 1 proton environment. Yeah, so and this spectrum has 4 peaks. So it's definitely not this one. But it's sort of unsure as to whether it's propan-1-ol or propantuol. And how you would tell the difference between those two things, that's when we would start looking at the integration traces underneath, right? The integration traces and our sort of splitting patterns. So won't the oxygen atom affect the two horizontal CH3s more than the polar CH3s? No. So do you mean like because they're closer to it? Because in the 2-methyl propantuol, if you mean because they're closer, remember that single bonds are fully rotatable. So those bonds won't stay in the same place. If it was like an alkene, then you might have a situation like that, where sort of like the actual arrangement matters, but as single bonds can fully rotate, then it doesn't matter sort of like where they are. Okay. If it's a concentrated solution, there's no chance of proton exchange, right? It really depends on sort of, there's no chance of proton exchange with the solution, with the solvent, but there is chance of proton exchange between the alcohols themselves. So yes and no. But yes, it does reduce the chance. Okay, I'm going to move forwards because we seem to be comfortable. So we could technically analyze this in terms of sort of like how many protons are in each environment, but I'm going to, why there are 4 environments there in the first one, because there's 2 CH2s. Yes, of course you can ask that. So I will say in a really low resolution NMR, the peaks would be so close together that they would sort of smush a bit and it would be really difficult to tell the difference between the two. But in a high resolution NMR, the CH2s will be very slightly different because one of them is closer in the molecule to a hydroxyl group, to that oxygen. So even though it's not directly bonded to a carbon that's bonded to an electronegative group, it's closer. So it's very slightly more shifted. So it has a very slightly higher chemical shift. Does that make sense? The spectrum is for, I'm not going to tell you. I'm going to wait till we sort of talked about splitting patterns. And then I'll tell you. All right, let's talk about splitting patterns because we are running out of time. So far, we've been totally ignoring the sort of fact that the peaks are not just like one nice line, they sort of split. So we're going to start talking about why they split. And so it's caused by an effect called spin-spin coupling, and they're only visible in high resolution proton NMR. So if it's really low resolution, you probably won't see the splitting pattern, but mostly we use high res proton NMR anyway. I'm not going to explain what spin-spin coupling is because there's not time and there's a lot of background knowledge required. So we sort of maybe one day I'll do a class on that on YouTube. We have had a class on that in our platform, but like we won't do that for now. Cool. So spin-spin coupling happens, it's an interaction between the protons on one carbon and the adjacent protons. So it's an interaction between those. And the protons on one carbon interacting with the protons on an adjacent carbon, that interaction causes the peaks to split. So the peaks split according to the N+1 rule. So I'm going to just start by sort of like writing some notes. So the protons couple with adjacent protons. So protons on a carbon next door, which causes splitting via the N+1 rule. So by N+1 rule, I mean, so for example, this carbon here, so the carbon circled in blue is this, not the splitting of the molecule, the splitting of the peak in those sort of like the wiggly peak patterns we can see on our diagram. So this proton, this hydrogen circled in blue, is bonded to a carbon that is adjacent to a carbon that's bonded to 3 other protons. So I'm going to circle those in purple. So the peak for the carbon in blue is going to have n+1 splits. Can I re-explain this? I'm not even done explaining it. People always do that to me. Like, I'm not even done saying what I'm saying. And it's like, I don't get it. Just wait, just wait. Okay, so the blue hydrogen is adjacent to 3 other hydrogens. So according to the n+1 rule, we take those 3 other hydrogens that it's adjacent to, add 1 because it's n+1, and that gives us 4, which means the peak for the blue hydrogen is going to split into 4 little peaks rather than just being one tall peak. Does that make sense? So the hydrogen in blue will split into 4 little peaks because it's next to 3 protons, and we just add 1. So it's n+1, so 3 + 1. So we'll split into 4 little peaks. So which peak is that hydrogen on the graph? Is it the one on the left or the one on the right? Is that hydrogen represented by the peak on the left or the right? Yeah, exactly. So this peak is the peak for that hydrogen there. So if it was next to 2 hydrogens, then there would be 3 peaks. Exactly, right? So if we sort of think about the purple peaks now, so here we've got 3 protons, and they are adjacent to 1 proton. So these 3 protons are bonded to a carbon that's bonded to only 1 other proton. So in that case, n equals 1. How would you know what n is? So n is the number of adjacent protons, and adjacent just means bonded to the carbon next door. So the carbon next door to this methyl group only has 1 proton, so n equals 1, and then we add 1, which means that the peak for this methyl group will split into 2. And we can see that here on the right-hand side. It's a doublet. It's sort of split into 2 little peaks. Is everybody following me so far? So it's about how many hydrogens are bonded to the carbon next door, and then you add 1, and that's how much the peak splits by. Are you guys following me? Wiggle, 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 wiggle. Yes, kind of. Kind of. Okay. All right. What can I do to sort of do more of these? All right, I'm just going to rub it out and sort of do it again. And then we'll sort of look at some more examples. So those 3 have turned into 1. Okay, so just to recap, remember that it's the area under the peak that tells you, I will give you a problem, but I want to sort of run through this really quickly again. It's the area under the peak that tells you how many protons are in that environment. So for our methyl group, we've got 3 protons in the environment. So that's going to be definitely going to be this peak, right? Because this peak says 3 on the top. So there's 3 protons in that environment. So that peak has got to be the one for the methyl group. But that you can see that the peak is split into 2. The peak is split into 2. And that's because the methyl group is bonded to a carbon that is bonded to 1 other hydrogen. And the n+1 rule says that if it's bonded to a carbon that's bonded to 1 other hydrogen, n equals 1 plus 1, again, because it's n+1, equals 2. And that is why the peak splits into 2. And you call it a doublet, and we'll come to the naming, more names in a second. So that peak is a doublet. The proton here, the one in the carbonyl group and the aldehyde group, there's only 1 proton in that environment, so it must be this peak, because we know that the integration, the area underneath, tells us how many protons are in the environment. So we know that there's 1 hydrogen in that environment, which makes sense, but this peak is split into 4. Why is it split into 4? So that's our spin-spin coupling again. So this hydrogen is bonded to a carbon that has 3 other hydrogens attached. And using our n+1 rule again, so n is 3 because we've got 3 hydrogens adjacent next door, plus 1 gives us 4. So that's why we have sort of 4 mini peaks under our splitting pattern. Those of you who were like, kind of, it makes sense. Is that making more sense? Yeah. What if there's 2 on the left and 2 on the right? So that's, you would still add them all up. That's 4 in total. So you would do 4 plus 1, and you would get 5 as your splitting pattern. Cool. All right. What I'm going to do is go back to the problem, our butanol problem. And I might as well just go all the way back here. I'm going to go back to our butanol problem, and we're going to start, which one is the left one for? So this left one, the one on the left, belongs to the carbonyl peak. It's for this hydrogen here. And you can tell that it's only for like 1 hydrogen. So only 1 hydrogen in that environment, because the area underneath it is 1, which it tells you up here. And it's quite short. So you can also tell that sort of by like just having a look at it. And it's next to a carbon that is bonded to 3 hydrogens, and you do n plus 1, so 3 plus 1, which is 4, which means that it has 4, it's split into 4 peaks. Wicked. All right, so let us have a look at this. We know it's not, we sort of decided that it's not the 2-methyl propantuol, but we've sort of got some options here for which whether it's butan-1 or butan-2ol, and the splitting pattern is going to help us sort of see that. So what I'm going to do, we're literally going to go through and figure out what the splitting pattern for each carbon would be. So ignore that that's in blue. So let's just start from the left. So on the left-hand side, we have a CH3, which is bonded to a carbon with 2 hydrogens. So what's my splitting pattern going to be? How many splits will I have peak? How many splits will I have for the CH3 at the end? Yeah, 3. And that's because it's next to a carbon that's bonded to 2 hydrogens. And so it's n plus 1. So it's bonded to a carbon with 2 hydrogens. So that's 2 plus 1, which gives us 3. So we'll have 3 mini peaks. Cool. I'm going to move on to the next one. So we have a CH2 there. What's the splitting pattern going to be for the CH2? So remember, it's about how many protons that the carbons next to it are bonded to, not how many protons there are. So you want to look at how many hydrogens are bonded to the carbons next to it, add them up, and then add 1. So it's not 3. It should be 6. So have a look. If you look next to that CH2, there's 2 hydrogens in the carbon to the right. There's 3 hydrogens on the carbon to the left. So you add those together and it makes 5. And then it's n plus 1, which gives you 6. So there should be 6. So I'm hoping the next one is going to make more sense to people. So we should have 6 splits for that CH2. What about the next CH2? What's my splitting pattern for the next CH2? The n is 2. N is not 2. Remember that n is the number of adjacent hydrogens. So the number of hydrogens attached to the carbons next to it, not on it. Does that make sense, Kang? So you're not counting the number of hydrogens on the carbon you're looking at. You're counting the number of hydrogens for the carbons that are bonded to that carbon. Yeah, so this one, there should be a splitting pattern of 5. So if we count the number of adjacent protons, we have 2 on the left, 2 on the right. So n is 4 plus 1 gives us 5. So that one would have a splitting pattern. Yeah, exactly, as there's 2 on either side. So yeah, so that would have a splitting pattern of 5. And we'll come to how to name those in a second. But those of you who are naming them now are fabulous. Cool. Does the alcohol group have a singlet splitting pattern? Yes, the alcohol group would be a singlet. and we'll sort of, but it's not on the graph. As I sort of mentioned before, the alcohol group is not on the graph. Where N equals the number of hydrogens on the adjacent carbon. Yeah, exactly. So what about this last CH2? What should the splitting pattern for this last CH2 be? Any ideas? What's my splitting pattern there? So Kang says 4. It's actually a triplet. So remember what I said about the OH. The OH hydrogen is not involved in coupling. It doesn't always show up on the graph. It shows up in random places on the graph. And it's also not involved in coupling. And that's again because it's labile. It can come often on the molecule. So it doesn't stick around very much. Why is it not involved in coupling? Because it comes off, essentially. Something has to stick around for it to sort of couple strongly enough to show on an NMR spectrum. And because hydrogens in sort of alcohol groups, in acid groups, they come off because it's slightly acidic. So they don't sort of do coupling. So this one, we will have a triplet because we're only counting the 2 hydrogens on that CH2 group next door, plus 1 is 3. It depends on the concentration, right? So the concentration will help it show up as a single peak. So it might be more likely to show up on the graph, but it definitely won't couple. It's the likelihood of coupling is very, very slim. But it might, increasing the concentration might sort of allow it to actually show up on the graph or show up more strongly on the graph, but coupling is quite unlikely for any labile hydrogen. It's not like never, but it's unlikely, and it certainly won't come up in A level. Does the labile rule apply to carboxylic acids? Yes. Yes, yes, yes. All right, so the question is, having a look at this graph and the splitting patterns on the graph, do we have butane 1-ol? Is this butane 1-ol? No. Nope. Correct. We should have butane 2-ol, and we're going to go through why now. Actually, I'm going to put my OH group up there. You don't see a 6. Yeah. 1, 2, 3, 4, 5, 6. There is actually a 6 splitting pattern. But we'll talk about, can I explain the labile bit again? Yes, I can, but let's go through why it's butane 2-ol first, and then I'll go back to that. Right, so I'm just gonna, because it's might be quite difficult for you guys to see on the screen, I'm gonna tell you that this has got a splitting pattern of 6. This has a splitting pattern of 5. This has a splitting pattern of 2, and this has a splitting pattern of 3. So just in case you can't see it properly. Cool. All right, so let's really quickly go through which of these splitting patterns sort of belongs to each of these hydrogens. So the CH3 on the left, what should the splitting pattern be? Yeah, so it's not butane 1-ol, it's got to be butane 2-ol, but let's sort of go through why really quickly. So the splitting pattern for the CH3, what should it be? Yeah, it should be a triplet. There should be 3. So the CH3 group must therefore belong to this peak. That's our triplet. There's 3. So what about the CH2 group next door? What's the splitting pattern? Yeah, 5. So it's bonded to the CH3 group. So that's 3 up there, and then it's bonded to that CH, which is 1. So together that makes 4 plus 1 because it's N plus 1, so it should be 5. So that CH2 group there, that belongs to this peak. So then the next one we need to look at is the CH. What's the splitting pattern for the CH? Any ideas? Yeah, there should be 6, right? Because it's bonded to a CH3, so that's 3 plus the 2 on the CH2 plus 1, which gives us 6. You're welcome, fact side. So we should have that CH belongs to the sort of sextet there. Yeah, and then the last one is going to be 4. Oops, because it belongs to our it's only bonded. Oh, it's not going to be 4. What am I talking about? It's going to be 2, people. Yeah, it should be 2 because it's bonded to a carbon that is only bonded to 1 hydrogen. So that's 1 adjacent hydrogen plus another one, that makes 2. So that's our doublet. So we definitely have butan-2-ol, right? Our spectrum perfectly corresponds to butan-2-ol. So really quickly, somebody asked me to explain the labile hydrogen one more time. So all that means, how did I get 4? I didn't get 4. I said, oops. And then I said, no, it's 2. Did not get 4. So just for the person that asked me to ask me why it's no labile, what that means again. So labile hydrogen just means one that comes off. So any group that's kind of acidic, so an alcohol group or a carboxylic acid group or an amino group, anything where the hydrogen sort of comes off as a bit of an acid sometimes. Sometimes that doesn't show up on an NMR spectrum, and it really doesn't couple. So it doesn't cause splitting patterns. But I'm just gonna, do we have time? I'm just gonna really quickly name the splitting patterns and then we're gonna stop. So that's that first one, a single peak is called a singlet. And just so you guys have it, and then we'll stop. The 2 splitting pattern is a doublet, 3 is a triplet, 4 is a quartet, 5 is a quintet, 6 is a sextet, and 7 is a septet. So if you speak French, you'll be all right for like the beginnings of the words, or if you remember some shapes. So a lot of the time, these ones are just referred to as multiplets. Or if it's like really complicated and you can't really tell what the splitting pattern is, that's a multiplet. What about the intensity ratio? So the intensity ratio just tells you, so that's called the integration ratio, not the intensity ratio. All that does is tell you sort of the relative numbers of protons in that environment. Because it's sort of not the height of the peaks that tells you how many protons are in an environment, it's the area underneath. And if the area underneath is particularly hard to just sort of like see by eye, you might get something called an integration trace, which like just shows you the sort of ratio between the number of hydrogens in a certain environment. So in this one, there's a 1-to-3 ratio. So yeah, like 1 to 2 to 1. Yeah, exactly. So this one's a 1-to-3 ratio. So there's 1 hydrogen versus 3 hydrogens in each environment. But I'm going to finish, people, and you've done so well. Well done, because I was not sure how popular these ones would be. And this has been like sort of a lot less of you in these classes compared to the others, and which makes a bit of sense because sort of this is a trickier topic and less people are sort of likely to want to stick around. Javier, yes, you can. So yes, so as usual, I'm going to do sort of like the pitch at the end, but well done, because this is a really hard topic. I like when I was at uni and actually like using this information to sort of analyze things in the lab, I found this hard to actually sort of use the NMR data. So I think it's just like, it's kind of important to get in there early and start recognizing things, because if you do chemistry in the future, this is like your bread and butter of analytical techniques. Yes, and it will prepare you for year 13. You're welcome. I am going to, what was I saying? Oh, show you the website. Huzzah! Yes, I'm going to show you our nice website, because that's sort of part of the reason that I come on YouTube, and then I'm going to give you the code. It was easy for you to understand it. Yes, so it's quite nice sort of understanding wise. It gets tricky when you don't know what the compounds are. So structure determination can get really quite hard. So when you're like given an NMR spectrum and told like work out what this structure is, so that is tricky. Anyway, I am from London. That is where I'm from. Cool. I am going to, what am I doing? I'm going to show you my website. Yes, I forgot what I was doing. I'm going to stop staring. Sharing my screen is the words that I meant to say. And then I'm going to show you our website before I go off to my next class, which is on our website. Blah, blah, blah. Okay, so this is our pretty website, if you haven't seen it. If you have, obviously you don't need to stick around for this unless you wanted the discount code. So basically what we've tried to do is make a website that has like everything you might need to do your A-levels, to succeed in your A-levels. So if you were to, for example, sign up for Edexcel chemistry, you would get, first of all, in sort of like the most basic package, like a bunch of sort of videos for all of the topics. So you would first do a diagnostic quiz, and then sort of it would pick out the topics that you aren't so good at, and then you could watch a bunch of videos to sort of like help you consolidate your knowledge, help you understand what's going on. And then you would do another quiz to make sure you actually understand what's happening, because sometimes watching videos, you think you get it until you have to do a question, and then you find out that you don't. And then you sort of could watch some exam question run-throughs to sort of give you an idea of what the questions are actually going to look like in an exam, which can be really useful. And then sort of like that's in our basic package. And then if you sort of have our pro package, then you also have these exam packs. Oh, I sort of skipped out on the exam packs. Going to do that. So we have our exam packs, which basically we've just come up with a bunch of exam questions for you guys to do, like literally hundreds, which took a really long time. And then we have like the solution to those, and sort of tells you like where you get your marks, any additional guidance that you might need to know. So like you can practice when you run out of the sort of past papers, because lots of students do. And that's sort of our pro package. And then if you want the ultimate package, as I say, you get me. You get sort of web classes with me. So in about 7 minutes, I'm going to be doing one on radical reactions and green chemistry. And we have like a bunch of other stuff. So like I'm going to be cycling back around to all of the year 13 stuff. Starting from next week. For this week, we're going to go through some organic chemistry, practical techniques, just stuff like that. Just normal classes and sort of drop-in sessions when you can just come in and ask me stuff. So that's our website. Sign up if you want some extra help, or if you just want more resources to do stuff, because that's what we've made it for. You're thinking of getting it, but your school does online live classes at the timing of the web classes. That sucks. That's really unlucky. I mean, it might be sort of worth sort of when the next academic year starts, when year 13 starts, if school is back, we'll probably be like shifting back to sort of like evening classes. So you could do that. But yes, that's rather unlucky with the timings. Okay, I think that is everything. Oh, apart from the code. I remembered. I am proud of myself. So guys, remember that these happen on Tuesdays and Thursdays at 3 o'clock. So if you would like to sign up to make sure that you get reminders about that, then if you just go to our channel, then you can set reminders for live videos. So you won't have to actually remember what happens when things happen. But if not, then just sort of like 4 o'clock, Tuesdays and Thursdays. I will be here. 3 o'clock, not 4 o'clock, 3 o'clock. And here's your code. Thank you for sticking around to the end. That was really tricky. And next on Thursday, we're going to be going back to the sort of normal setup where we just go through exam questions, and it should be on alcohols. So I will see you then, my lovelies. Have a nice afternoon.